is Professor Federated Ablayev. He is an academician of the Academy of Science of the Republic of Tatarstan. He is the head of the Department of Theoretical Cybernetics, Institute of Computational Mathematics and Information Technology, Shenzhen Federal University. His talk title is Effective Quantum Algorithms for the Dictionary Search Problem based on quantum fingerprinting-hashing technique. So Professor Federated Ablayev, he's going to be online to present his talk. Let's welcome Professor Ablayev.
Hello.
Yeah, you can go ahead. Thank you. So can you share your screen?
For that moment. So it's, in any case, I am grateful to organizers of the first symposium, to the chairs. So I am so grateful that we start this first symposium, joint symposium, and so it's. I also would grateful to Professor Joshua Huang for our almost decade collaboration in area of computer science and quantum computer science, and so it's. I would like to present my talk, which is joint work with my colleagues. Do you read me? Do you hear me?
Yeah, we can hear you, but we cannot see the presentation. Can you share your screen? Yeah, can you see our shared screen?
Hi, Farid.
Okay.
You can start to talk about your first page from the title page. You can start now. Just start talk. Okay, we will turn your slides.
Yes.
Okay.
So I can start talking.
Yes. Start talk. Yeah.
Yeah. So it's okay. Then okay. So it's the first slide is so it's introduce our group. So it's we are working. It's joint group from Kazan University and Kazan Physical Technical Institute. So it's now please the next slide, please, the second one. So it's the problem is just to organize effective search in dictionary of n elements. So it is known classical results in this area. So it is known that when a dictionary is ordered, then we can organize a very effective and fast search just using log n queries for the dictionary. But when we have an ordered dictionary, then the problem is we have a problem that we cannot reduce our search and to have less than ON queries. So it's the search is linear in the size of the dictionary. What quantum technology allows for this? It is just allowed to have the result with a high probability and to have only square and query steps for this kind of search. So it's and it is this is well-known result in quantum algorithms, and this result is strict. So it's low bounds also proved by a group of mathematics in more than 20 years ago. So now let's go to the third slide. Third slide is just formalization of this problem for the case when we have an ordered dictionary. So, the example of such a problem is finding a word in a string. So we can also show this, that this can be done as an ordered dictionary search. Now, please, the slide number 4. Slide number 4 shows that the previous classical and quantum result in this array. So you see, classical result is well known in the 70s, proved by Knuth and Rabin-Karp in 87. So the search is fast. It means that using a vocabulary of size n, and when we have the word of length m, to find the occurrence of this word in the vocabulary needs n plus m steps of computation. And it is important to outline here that these classical results, which are well known now, they use the technique of hashing. Hashing is important here for accelerating the search in dictionaries. So what about quantum? So you see, during last 20 years, 2 decades, there are several attempts to have good algorithms which where quantum technology can help us. So you see, we have acceleration of the search. It's square n plus square m and so on. And so what is important that the use of memory in all of these quantum algorithms is the following: log n plus m. Log n, it means n is the size of vocabulary and m is the size of word. So now the slide number 5. So okay, let's skip this slide number 5, and I will go to slide number 6. Slide number 6 shows our result. So we just apply technique of quantum hashing for this problem, and this technique allows us to exponentially save quantum memory for this. So we have the following result for the space. We need log n plus log m qubits for organizing this quantum search, and the speed of just number of queries are the same as we had before, square n. So the main result is that we now quantumly save qubits, exponentially save qubits. So now let's go to the slide 7. So, now I would like to show the ideas of the algorithms. We have 2 types of algorithms for this, and so first part of the algorithm is the following. So we have vocabulary V, which contains of n words, and we organize randomly, uniformly. We choose some prime p from the first p d primes, and organize the vocabulary according quantum state according to selected prime p, which is randomly selected. So we have uniformly distributed random quantum states, which are described here. These are VP, quantum state, where the word W, each W word represented by a reminder RV in for this dictionary. So it's now the slide number 8. So it's and the second part of the algorithm is just applying Grover queries for this, and using these Grover macro steps, we with a high probability will find needed word. So it works perfect here. So we can just generalize this this kind of idea as the following. So it's please the next slide 9. So it's the algorithm generalized as the following. We just use the family of universal hash functions, which are universal hash functions, and it means epsilon universality means the following. So we have small collisions. Collision is the case when two different words are give the same hash. So this is known as collision, and the idea is the following. So it's the universe, family of hashes are universal hash family if the collision for each pair is small. So and for our algorithms, we need a slightly generalize this idea of universal hashing. Please, slide 10. And so we generalize this as the following. So the collision should be very small. So it's not only small, but very small. It means that when we fix any set of and subsets of words, then the summarizing collision should be very small. So this is the idea, and it works. When we use the now the slide number 11, and when we use this kind of family of universal hashing, then we generalize the previous idea, which I demonstrated by the example with reminders, and it works perfectly. And now the slide number 12, that the result we have is the following. So using this kind of hash family, we can we go into the Grover's condition of applying Grover algorithm, and it works perfect. And we have the following number of qubits which we need: log n plus L, where L is the way of hashing input words by L qubits, and the error is very small, epsilon plus 1 divided to n. So this is the idea of this this algorithm. And please, the slide number 13. Slide number 13 shows that our result is published recently in December in in Journal of Mathematics, and here is this paper. And now slide number 14, and this result now we present another algorithm for quantum search in dictionary. And here we use exactly idea which was developed and go on developing in our group on quantum hashing. So it's we call first of all what kind of function we call quantum hash function. So it is the following function. So we have the m word dictionary, m words we compress into s qubits. So it's and we call this kind of mapping epsilon orthogonal if arbitrary different two words are almost orthogonal, epsilon orthogonal. This property is the following. So it's when two quantum states are orthogonal, it means that they are perfectly distinguishable. When and it means that then no collision. It means that there will be no collision in the following sense. So it's okay. So it's in quantum case, in pure quantum case, we have the following. So it's there are no collision in quantum world, but we can by mistake when we measure this kind of states, we can have an error and we can recognize one word as other word with some probability. So this is the collision in our sense. But when the states are almost orthogonal, then it means that the probability of collision is very small. So this is the idea of quantum hashing. And so it's what we have here. If we would like to hash functions, words of length m, which should be perfectly hashed, then so it's the probability of error should be small, epsilon. Then number of qubits shouldn't be less than log m. So this is the property which we have here. So it is also known. So we have some restriction for this. And now let's go to the slide number 15. Slide 15 shows that now we use the idea of hashing, of presenting quantum state from vocabulary as the following. So it's first of all we enumerate all words. So this is the first group of qubits. Then we add hash of each word, and so this is the quantum vocabulary of for which we organized the search. So it's now the slide number 16. The search will be organized as the following. When we have the word which we are watching for, then we should do the following manipulation. We reverse a hash function. So I said that here in quantum word hashing is 1-to-1. So it's then no collisions in quantum word, but collisions appear only when we would like to measure the result. So it means that in quantum world we can reverse quantum hash function, and there is and it has the very important property that if when we hash we when we reverse our hashing, then we have we get a new quantum state which is organized very in very good way. So it's the target function, the target word will be appeared with a high amplitude, and other words and other states will appear with a small amplitude. So this is the key property of for hashing here in this result. So it's, and so now the result, slide number 17. So it's when we do this first step of stage of amplitude amplification, then after this we can just use known amplitude amplification steps, which is known as Grover macro steps of amplitude amplification. And finally, we get result, needed result index of the word with a high probability. So, and now the slide number 18. So here we have theorems which summarize the property of algorithm described. So it is proved, and so we have normal formal proof for this. So everything is based on different description of not different, but descriptions of quantum hashing. So it's, and we have publication on this recent publication. And so it's now the last slide is 19. So it's we just recently put all this result together and published and presented in archive. So and the last slide 20. So thank you so much. So that's all. Thank you so much.
Yeah, thank you very much. So any questions? Yeah, okay. We have one question.
Oh, hello. Thanks for wait. So I'm Chin Chan Edison from Shenzhen University. I would like to ask you two questions regarding this topic. First, as you know, we have the RAM model and also quantum model, right? So RAM
yes.
model, you know, there are maybe P, class P, MP, exponential class. So in quantum computing, do we have this kind of classes? And this is the first question.
Yeah, so if I correctly understand the question, so it's in search problem, quantum algorithms help much, and it's allowed to accelerate in time, square root in time search procedure. But before hashing, so it's when known quantum algorithm used for this, they use a memory which is log n plus m, where n is number of words in the vocabulary and m is the length of word. So it's, and we apply quantum hashing for this kind of search, which allows exponentially save quantum space for this, for this kind of search.
Okay,
so
thanks for answer.
This is the first step. So it's the next step which we are going on working on this. So it is known that it is important problem to search in vocabulary is approximate search in vocabulary. So this kind of approximate search used in clustering algorithms in big data searching. So it is one of the important things there. So it's, and now we are finishing our word, which where we describe our algorithm for approximate searching in vocabularies.
All right, thanks. So another question is that I would like to ask is, you know we have the MP hard problem, MP complete problem in the RAM model.
Yes.
So
yes.
So you know in a quantum algorithms, normally those algorithms the time complexity can be much lower compared with those in RAM model. So So is it possible that some NP hard problem in RAM, I mean, in RAM can be much better, and maybe I don't know because I do not know the
So it's okay. This is the open problem that quantum algorithm can solve NP hard problem. So it's open. It's open. So it's the one of the most known and useful algorithms are Fourier transform, quantum Fourier transform, which can exponentially save the time. But so it's open for to apply it for NP hard problem. But Grover algorithm, which is widely used in database search, is just allowed to save search, which is on the square root, not exponentially, but the square root.
So does it mean we still do not know that whether there's some exponential time compressed algorithm can be reduced to the polynomial time? Is this?
So I don't understand.
So that's me. I know. That's me. What I mean is that the NP-hard problem, for some NP-hard problem, the algorithm in the, I mean, if you develop some quantum algorithm, it's still unknown whether it can reduce the time complexity to polynomial time. Okay. Thanks for answer.
Thank you for your interest and report. My name is Nechosov Andrei from Novosibirsk. I have some questions. What about main questions of crypto society for Bitcoin collision? Can we use a quantum technology decide this problem with collision when we use a hash can find an initial word?
It's interesting. Okay, that's interesting question. So recently it is announced that Bitcoin problem, which is used SHA hashing, is secure for the current technology of quantum computing. But so it's I guess in something in 10-15 years it will be secure, I guess.
Please, I repeat your last sentences. 10 years and you will in currently 10 years it will be security. After that you cannot guarantee, yes? This security.
Yeah.
Okay.
No. Yes. Nobody, but during these 10-15 years, I think we can use Bitcoins for free. So not for free, but securely. So it's
okay. Which times quantum computer can accelerate of total power of standard computers? In which times quantum computer can move faster?
Yeah. I understand the question. So it is well-known problem when we are waiting for any problem to find any problem which can be solved faster by quantum compared to classical one. So it's one of the first such steps Google did several years ago, and it announced that they found a problem which can be solved faster than the classical one. But then it is appeared that more clever classical algorithms were found for their problem. So it's the problem is still open to find any kind of problem when modern quantum computer can can solve it faster than the classical one. So it's that's open, but you see, technology goes fast, so fast, and so it's nobody can say at the moment that, for example, this kind of problem will not be found. So it's, and
okay, thank you.
But here is important that hashing SHA hash function, which is used for bitcoins, they will be secure at least 10, 15 years. So it's,
okay, thank you very much, Farid.
Thank you.
Yeah, thank you very much. Quantum computing definitely is a very interesting topic. So you guys can have some other ways to do lots of information exchange to get more on the latest advancement of this technology. Our next speaker is Professor Yi Pan. He's a fellow of American Institute for Medical and Biological Engineering, member of European Academy of Sciences and Arts, fellow of the Royal Society for Public Health, chair professor and dean of Faculty of Computer Science and Control Engineering at Shenzhen University of Advanced Technology. So let's welcome Professor Yi Pan. He's going to give a talk on AIGC Empowers biomedical applications. Let's welcome Professor Pan. Thank you.
Professor Zhang, thank you very much for your introduction, and thank Professor Huang for your invitation. Today I learned a lot from Professor Sergey and Professor Xu. Professor Xu is my older friend for so many years. 40 years ago, we were graduate students at Tsinghua University then. So now we met again, and I learned from him a lot. His neural net contribution is great, influential, and world-class results. Now, I'm not an AI person, but I applied AI in biomedical area. So let's introduce a little bit about my research in this area. So you can see here, is this working? It's working? Oh, yeah, it's working. Okay, so currently I'm talking about the AIGC. Why AIGC suddenly is so interesting? Because AIGC can be used by normal people. Before, Professor Xu's results only you can say male, female, dog or cat. Now, we can generate material, generate image, generate video. So common people can use it now. So now it's popular. That's why it's an explosion of AI, right? So refreshing our AI, now AI is in the past, we have a lot of AI history like Professor Xu already talked about. But now this is a hot topic because time limited, I don't want to talk to this too much. Large language model, right? When we talk about neural net, what's meaning large language model? Basically, you have generative results. Also, large means what? Means over 100 billion parameters, right? This is called large. So here, Tsinghua University, Google, everybody has large models. And in China, Baidu and Huawei also have models. Wenxin Yihao is Baidu, and Huawei have Pangu and so on, right? And Tianqi is also from Tsinghua. He's doing well at Huawei. So the model basically by Huawei is basically, you can see here, they're divided into functionality, function, computer vision, natural language processing, and so on. However, I like this model more interesting. Level 0 fundamental model, meaning all the data are from common internet, right? So you train the model, so it becomes basic model. Now, with the basic model is not enough. You need to go up to what? Go up to little bit to area, discipline. For example, medical area or co-binding area or transportation area and so on. Then further go up, L2 really means what? If you have discipline area, still not enough. For example, medical area, we are talking about the drug design, you're talking about disease prediction, still different. You need to further go up. Wherever you go up a little bit, you put the knowledge more, you adjust to the parameters, the model is more specialized. Clear? Right? So special. So actually, I further propose you should go to L3. L3 means what? Problem-solving model. Because even though in the same discipline, same area, if you're using different technology to solve the problem, you need a different knowledge, right? So I use L3, right? I didn't put this slide there, but in Chinese slides, I already changed this. With this one level up, you put more specialized data, you train the model, you get a better local knowledge, right? So when OpenAI, ChatGPT proposed, suddenly become hot. In the beginning of 2023, I predict many stuff can be used for association. For example, protein function prediction, gene disease association, and so on, many. But I want to put some ideas here. First is called federated AI. It's different from federated learning, right? Federated AI means what? I always propose, right? I propose bigger model cannot sustain forever. Why? Because they consume too much electrical power. So we need actually small model. Smaller model save money, save power. Now, smaller model also have problems suddenly. For example, if we are talking about poem generation, right? You just put a lot of poem training, that's all, right? And generate a new poem, right? If you are talking about medical, you just put a medical information, generate a medical, that's it. However, still have shortcoming. For example, let's say law GPT. If you are a law student, you have law GPT, both Professor Sergey, okay? So you use law, right? GPT working fine. However, in law problems, certain time you associate with a medical issue, certain time with a transportation issue. How to solve the problem? In Chinese, we say, 3个臭皮匠合成诸葛亮. 3 smaller model to combine together to solve a big problem. Still save money and still solve big problem. The next question I want to propose is what? It's called time sharing big model and plus smaller model. So Professor Sergey, you have small model. Locally, it's fine. You are using not too much GPU, you save money. However, whenever you need some information not locally available, you go to ChatGPT. But use what? Only 1 second. Now using 1 second, you save money, right? You don't use consistently. 1 second, grab the information, combine with your local smaller GPT, smaller model, and you solve the problem. So this is my proposal, and we did it. Now OpenAI Sora is more interesting, and I want to emphasize what? Physical model is important now. In the past, we always parameter-driven, right? Data-driven model. For example, Sora, you have a short video. You can see the lady's clothing, right? Suddenly, a butterfly come in and leave immediately. Why? Because no physical model restriction. Because the butterfly cannot go to Professor Sergey now and suddenly within 0.01% second leave immediately. Impossible in reality, right? But they did. Why? The connection, the combining of this patch has problem. So we need to enforce physical model there. So in the future, I think is, I always propose the idea is what? In the future, knowledge. But the knowledge, where's knowledge? One is knowledge from our brain. Second, knowledge from what? Physical model. Physical model is important. To put the physical model into the neural net is important, right? So here I want to propose 3. Besides discussion of this, I want to propose this idea. So in the past, people always say big language model have 3 forces, right? 三驾马车, data, algorithm, and what? 算力, power, computing power, right? Actually, 2 years ago, I proposed already 6 parameters, 6 measures. The other 2 are important knowledge. Why important knowledge? Important knowledge is important because theoretically, right, even though 100 billion parameters for a big model, right, our brain's parameter is 1,000 more times than other bigger model. So our brain's knowledge is more useful, more powerful. Actually, that's why we can put, it's important to put our brain's knowledge inside the big model. Another one is called what? Interpretability. You need to interpret the data, right? And the last one is the low energy consumption. So 6 measures, low energy consumption, also important. Now, I proposed this idea a few years ago, right? Professor Zhang Bo just proposed the idea this year. He said, Professor Zhang Bo is the most famous professor in AI in China, similar to Professor Xu Lei, right, from Tsinghua University. He said, 三驾马车不够, you need to put the knowledge. So I proposed before him. And the last one, Elon Musk last year said, in the near future, GPU is not the issue. Actually, the power is the issue. And I proposed before him, right? 2 years ago, I proposed. Elon Musk proposed this idea only 1 year ago. So, a few months ago, a kid from USA, her mother brought him to see 17 doctors, no cure, no method. So he has trouble. So his mother typed the symptom into ChatGPT, and the ChatGPT gave him an answer. He said, maybe this is a disease. And he put the disease, take the disease name to the doctor. Doctor said, yeah, maybe makes sense. And can prescribe medicine, cure this problem, right? So this means in the future, ChatGPT can cure, actually diagnose your disease. Certain time you don't have to see doctor. At least at home, you diagnose yourself first. However, another study show it's not perfect. ChatGPT gave you, for example, this is a cancer management issue. The correct answer is only 62%. The others are incorrect. So now we are in an era with using ChatGPT. However, ChatGPT also gives you wrong information, certain time correct information. How do we handle this issue? So this is the detailed analysis, correct and incorrect information. So in the near future, I believe we have to heavily depend on AI checking program. For example, in USA, they have a GPT-0. They check for you, is this wrong information? Is this correct? Is this consistent? Is this fake information? Is this from AI generated information? So on. In China, Chinese Daily also have a software called AIGC X. This AIGC X also show, this is information from older newspaper, or is it original, or is this a fake, or consistent, and so on, right? Now, my student in Hangzhou generated this Jun-Tong technology. You can see here a picture. You change your head, his software can detect, oh, this is fake image. The video, you change the video, the Liu Yifei video face into there, he can check immediately this video is a fake. Also, step you Tsinghua become Beijing University, he say fake, right? Article, he can say fake, and so on. So his last 2 years ago, 2023, his revenue is already 10 million RMB, 10 million yuan. And this year, he just reported to me the revenue is already 30 million yuan, 3,000 万. So meaning this trend is really good. Whenever you need to check your results generated from OpenAI or other software, AI software, right? You use his software to check the authenticity of this data. And so this is a booming business in the future. I believe AI, you have to use this. Now, AIGC, of course, in biology, we can use a lot of areas. And I want to show one is what it's called the question answering system. Now, this system, question answer system, a long time ago, we already have this, right? The only difference is we want to beat ChatGPT, right? Our system specified specifically for autism disease. So in the future, for example, if I have a cancer question answer system, Professor Sergey asked me, right? Cancer caused by what? This system will answer you correctly, right? This is caused by gene, which gene? We will answer it correctly. Now this system, I want to show you our system working? Again, follow my source, right? My source is what? Big data driven is not enough. You always need to put specialized knowledge in the system to make the system better. Now, I'm going to show you how to do it. So in the past, answering question system, you can use NLP, natural processing language, or question answering system, have some problems. If, for example, this Q&S have limited understanding, poor flexibility, and so on. Large language model ChatGPT also have problem. What's the problem? The big problem is big data driven is good. However, hallucination, right? Hallucination is big problem. Right? You know, generate fake results, basically. Even though they don't have the knowledge, they just generate something related, right? So a typical example like Hong Shao Wenzi, right? They give you the menu for cooking a fly even, right? Fly, mosquito even, right? So it's a fake. Because if they don't have knowledge, they just generate something which is incorrect. Our system is based on large language model plus RAG, retrieval augmented generation. Now, you know, RAG basically is local knowledge, special knowledge. Now, let me show you how do we do it. Here, we put over 200 papers in autism disease only, and 30 documents, government documents related to autism. We put this knowledge inside this system. Now, our system, of course, we have to use open source, right? We use Llama. Llama is open source. So the basic model is already trained. We put the RAG there. Now, you can see here, in the past, OpenAI, basically, you ask a question, data-driven, however, in our system, we question, you go to the documents, because 330 documents, right? You retrieve these embedded knowledge and the related information, and then go there and generate the results, and then go up, give you the user. So now you can see what our results are different from the traditional ChatGPT, in this case, Llama, right? So we use 6-dimension measurement for accuracy. So why my system, Sergey, you have a system, I'm better than you, how do you measure? We use this 6 measure. Now, of course, you can change, right? But at least accuracy, difficulty, relevance, and so on, we change. We also use typical 145 typical questions asked by the mother most time, right? These are provided by doctors, right? And now we show, for example, typical question. What are the potential genes that may be associated with autism? The guy from Tsinghua Chat, GLM, they cannot answer. Basically, they have no knowledge about it. It's irrelevant to answer, basically. This guy have relevant answer, but the gene is incorrect. Because hallucination. They don't have a solution, but they have to make up the gene, right? The name. Our answer is correct. Now, whenever I say I'm better than you, use one question answer, I'm correct, you are incorrect, I'm not better than you yet, right? You have to use statistically to say, most time I'm accurate, I'm better than you, right? So we use all these questions, 145 questions, experimental results. The red one, accuracy results, the weight is better than most of them, better than Tsinghua's, better than the ChatGPT, better than Llama, and so on, right? This shows large language model is good. However, if you put specialized knowledge there, you can have perform better results in this case. Now, in the future, some company already give me say, Professor Pan, do you want to money invest? Because we can expand the idea. For cancer, we have another question answer system. For heart disease, we have another question answer system. Actually, our system probably potentially can replace many clinics. Low-level doctors, at least better than them, right? So this is one example showing knowledge is powerful. Our brain knowledge is very powerful. Next question, I'm talking about AI drug design. AI drug design is very interesting, right? Take a long time, take a lot of money, and still very hard to design. And so global market is big for AI design. And so this is year is long and $1 billion spent on AI. However, we have a lot of data, pharmaceutical data, gene data, and so on. And can we do a better results, right? And I hope in the future we can do a better results. So I can, because time limited, I can show you only some slides and this one. For example, this is talk about the COVID-19, right? COVID-19, this is human cell. Actually, we are going to design this drug to blocking this cell so the virus cannot come in. How to design this issue, the molecule, right? And I always use this example to show people what's the meaning here. So here, this is a lock, it's a target. So biology people tell me this particular protein is the target, meaning what? This target can cure cancer. This target can cure heart disease. This target can cure influenza, so on. Now, this is available already. What we need is design a key. Key basically tightly combining with the target so that you can inhibit this disease, right? This is the case. Now, in the past, suddenly Professor Xu said, hey, Professor Pan, I found a new target for cure disease. In the past, how do we do it? We have millions of molecules. You have to test. Is this working tight? Is this working tight? Most time fail, and working, then you can continue development. What meaning AI? AI basically, we don't need to do biological testing. Millions of biology molecules, we just testing. Are they close enough, right? Close enough, we say yes, keep. Otherwise, throw away. Then I will show you, is this working, right? So first our paper is basically this is 3 papers, and I'll give it a detail. So this is a neural net, and this target. And we basically use positive examples, negative examples, and show which molecules will combine with this one tightly. So this is very simple, similar to a couple, right? Prediction. Here, there's a man here, and we have a 40,000 women. Can we predict their marriages good enough? Use AI, right? Positive example means successful marriage example. This male, this female, high salary versus male, female also high salary. Looking good, and so on, right? Height, and so on. So we show our software really can do this, and you can see here, we precision is better in our tool, and then we found some molecules which cannot be found in other software. Now, let me show you one example. This is the example, basically, is type 2. Type 2 is for cancer. Can we find a small molecule, right? So I can show you this one example. So type 2 is this target in. And we use 8,888 molecules. Now, why 8,000? Lucky number, right? We can test in millions, right? Lucky number. Then using this software, our software, we reduce to 421. Then this meaning 421 very close, tightly binding. Then we use molecular dynamic simulation to measure the energy. Now, if they're tightly binding, if the energy is high, they are like this. Energy high is like moving around, not good for a drug. Throw away. If the energy is low, means very cold, right? Energy low, they are tightly and also not moving around. Very good for drug. Keep. So we reduce to 69. 69 reduced, then we testing only the top 4, we find 1. Many people ask me, you select 69, why only testing 4? Because each testing, biological testing, costs me too much money. I don't have the money. For paper, at least test 4, found 1 enough. If not found 1, I test 5 or 6. At least find 1 enough, right? And you can see here, we find 1. Out of the 4, we find 1, the affinity is only mu n, 4.9 mu n, meaning which is close enough for potential drug. Is that clear? So don't have time too much, and this is for drug design, right? Last one, I want to show you the generative information. AIGC means what? You can generate an article, you can generate a poem. Here, actually, we are before ChatGPT. We generate a drug. Now I can show you. So here, you import something, and then you say, okay, about immigrant, then this poem, A, B, C, D, already done, right? And here, you about love letter. This guy generated a love letter, A, B, C, D, right? This is very good. In my opinion, we can do similar thing. This is the black box AI. And the input is what? If you are Shuzumo's poem, this poem generate a new poem, right? Professor Sega, I generate a new poem, give to you, you say, Dr. Pear, I don't like it, it's garbage, because it's a combination of words, right? However, I ask you, if I generate 1,000 poem, maybe you say, oh, this is fancy, right? So, similar thing. We imported what? A few thousand of molecules related to cancer. And the cancer is what? The molecule basically is what? Sentence. It's a words combination, right? As you said, protein, DNA, right? It's coding. So this coding import, we grab it, change, generate new coding. Is this potentially drug? It's possible, right? So I can show you now. So here, you basically put the chemical database here, millions of chemicals here. We transform a GPT here. We generate a new drug, small molecules. And without filtering, of course, garbage. If I give you 10,000 poem, you say, I don't want to read it. Most are garbage anyway. But if I have a machine, give you 10,000 poem, you have a machine to test. This is good poem. These are bad, maybe useful. Is that your similar idea? We have a filtering system. We can filter. You generate 10,000 small molecules. Most are garbage. However, we filter and then screening and then talking and then found. So this is called what? Drug design now. Before it's called drug filtering. Now really drug design. Now in the whole world, we only have about 10 million small molecules in the existing physical system. However, with AI generating molecule, how much? 10 of power of 30. The space is much larger. So in the future, non-existing small molecule drugs, now we can use AI to generate, potentially fit in, potentially filter, potentially become a drug. So this is the idea. And I can show you here, we can, not too much, we can show you here. 3 papers you can see. One is published 2020 July, and this is 23 February, submitted 21. Meaning what? Before the hot of ChatGPT. So our idea is before AIGC become hot. We already have ideas. Generate small molecule become design. Right? And I can show you our paper. Basically, we put these related molecules, go in, and then generate the procedure you can see here. Like a poem, right? Generate this one, become 23, and the 23 poem go back 48, and go back with the original poem becomes 400. Now, if you want to generate 10,000, whatever, you can do, continue, right? Because this is a combination of something, right? Of course, in the future, if you use drug knowledge, use molecular knowledge, use this kind of knowledge, you can generate a better one, like a poem, right? Not like a random combination. You have knowledge of the poem. This poem is beautiful. Why? Because these combinations are beautiful. These should be adverb, become noun, then whatever, right? These rules put there become, and this is just a preliminary result, right? And we can show here filtering and so on. Finally, biological testing show this is a real drug. And you can see here, using generated AIGC, we already find some molecule which is used for SARS-CoV-19. Right? So this shows our software is really effective, right? And this is another similar thing on this one. So in the future, I hope right now drug discovery use AI, basically small molecules. In the future, testing, biological testing, digital. In the future, digital ops. And eventually, if we have a digital human being testing, of course, this is in the far future, right? then we can avoid this kind of human testing and reduce the cycle and drug designs. Thank you very much.
Yeah, thank you very much, Professor Pan. Any questions from the? Okay.
Professor Xu, fundamental researcher.
It's a very interesting talk. You give several interesting topics, but I mention just one thing. You talk about federal AI. I suggest you really try to build some kind of actually federal, MOE, and all this is a current very hot thing. It's a tendency. I suggest you make that just a platform or a system. Try to open, make it AI open. You talk is similar like I mentioned DeepSeek. This DeepSeek recently become very hot. Successful also try to divide into many small experts, very accurately small, you call small model, they call experts. It's a similar idea. It's currently, it's go to this. Just a few days ago, I have some kind of interview by Shanghai government or something. I talk also like this. I mention my idea, my point is like this, my opinion. So-called large model, past few years, then everybody talking about scaling law. Then it's meaning go large, go large, go large. When this go large, now even you increase this kind of chips, increase the computation power, you don't have enough data, then you don't successful. It's the first stage. That is just we AI develop into provide the room, provide the necessary condition for. But next step, just like a brain, you have a brain. You need to develop many different function area. You need to go. That is you call the federal. So now, second stage of a large model, just what you did. You already did. So I suggest you try to put your federal AI model in medical diagnosis, those kind of things, into a system to try to quickly try to open it.
Great.
Then everybody know your system.
Yeah, very good comments, Professor Xu. Actually, also my close friend, his friend also, Xue Donghuang from Microsoft. Now he's a CTO at Zoom. He tested the system, Federated, similar idea, right? He used 3 smaller system, smaller model, and combine together generated results. Similar results with ChatGPT. However, the power consumption only 1/10 of ChatGPT. So he shows really working model. So Professor Xu, maybe we'll discuss with you more about these kind of schemes. Yeah.
Okay, definitely you guys can work together. Just one thing I want to mention about Professor Pan. He was the only department chair of computer science and the department chair of the bioengineering at Georgia State University. So he served both chairs. So he has a lot of background or experience on the both aspects. So you enjoy, thank you very much for your talk. Yeah, you guys, if you have any questions, you can talk to him offline. Okay, thank you much.
Thank you, Professor. Thank you.